Hello and welcome to another session of classical motion of a single particle. So, in this discussion we will be elucidating some concepts which sometimes we are getting confused with. This is the concept of the energy diagram, or I mean sometimes we also say like a potential well and the potential picture. Okay. So, this is this is an elementary idea which I think that every physicist should understand very clearly, so that the analysis and the nature of motion under any potential which be very clear. Now, of course, in this discussion we will be constraining ourselves to the case of a one dimensional motion, but as I told you, this course is mainly dedicated to the case of motions which are valid for more than one dimension. So, if of course, we do more than one dimensions, then according to the vector formula or vector property of Newton's law. So, basically the point is, if you know how to analyze that for one dimension, then you can do the analysis independently for the three components in a three dimensional space, for example, or in a two dimensional space for two components, and then you can conclude. Okay. Now, I start by saying this thing, that let us say a particle is moving in one dimension and the particle is subject to a conservative force field F x. So, F x is conservative, and that is why F x is equal to minus du dx, and this u x, which is the potential, of course, du of x only, and this u x is actually plotted along this y axis here, and along the x axis I plot x. Now, this blue curve represents the potential curve for that particle at different x. So, let us say this is a some function. So, this is the u x, and this is exactly representing the potential function at different x. So, this is the u x. Okay. Now, the point is that we want to know the nature of motion, or nature of state of motion, or the somehow the kinematics, nature of kinematics, some global conclusion about the kinematics of the particle under this potential. Okay. Many a times whenever I talk to informally talk to students or some people, they think that in this diagram there is a particle which is actually simply physically moving. So, this diagram, first of all, this is not a diagram, not a diagram for the real time motion of a particle. That means that let us say at time t is equal to 0, if the particle is there, and at some posterior time if the particle is there, and then you cannot always conclude that again at a posterior time it will be actually here. Okay. So, that is because that is simply by saying that here we will just find the displacements or the variation of the displacements and the variation of u x as a function of space. Here we are actually not looking at our watch that at which time at what distance the particle is, rather we will just we will be happy to understand what is the displacement and what will be the corresponding potential energy of that particle. So, this is this plot. Now, how to understand the global nature of a particle, of the movement of a particle from this type of diagram. Let us say I am now trying to first analyze the nature of this potential. So, this potential you see, it starts from a very high value when x was negative, and then finally it decreases and it crosses 0 and attains a local minimum, and then again it increases, and finally it is asymptotically going to ux is equal to 0. So, asymptotically it attains to 0 value for infinitely large x in the positive direction. Okay. So, for the first as a first step I have to conclude that this motion has one stable equilibrium position. Because this is the minimum of my potential energy, and from that I can actually calculate. So, if I know the functional form of that u, I can actually explicitly calculate the x and the value of ux at that point, okay, and that will be of course ux minimum. Now, I am given some energy of the particle. Okay. So, I am now saying that I am now considering the particle which is having a total mechanical energy equal to this value, let us say E1. Okay. This y axis of course ux is plotted, but this y axis is actually carrying any energy, energy unit of energy. So, any energy can be actually plotted based on this y axis or on y axis as a function of x. So, I am just plotting now the total mechanical energy. Now, the total mechanical energy, as you understand, this is a conservative force, it will not change ever during the motion of the particle. So, for all x its value is actually constant. So, the next conclusion is half m v square plus ux is equal to E1, which is a constant. So, if I somehow make my system with the total mechanical energy initially is equal to E1, then after the starting of the motion, when we just do not care about the about the time instants, we will at any arbitrary time instant, if you just check, the total energy is constant at this value. But the potential energy is not the same at every point of x. Okay. So, let us say now at some time instant, we do not care about that time instant, the potential, the particle is actually at this point. What happens? So, that is the displacement. Okay. So, from some origin. Okay. So, the particle, so let us say I am now, if I just plot over here the real time motion of the particle in this x direction. So, let us say this is origin, and let us say after some point the particle actually is having some, and this is minus x direction. Okay. The particle is having actually this amount of displacement, which is let us say some minus x 0. Okay. So, this is here I can also set as x is equal to 0 and this is minus x 0. Okay. So, then of course, at this point the particle has some velocity and has some potential energy. Now, the potential energy is actually given at this point by this, by this amount. Okay. So, at this point the potential energy is given by this amount, because if you have minus x like this, so the corresponding potential energy will simply be u of minus x 0, and which will be simply given by this point, this is u of minus x 0. Okay. Now, this is the potential energy part, this is the total energy part. What will be the rest? What will be the gap between them? U1 minus ux, that will be its kinetic energy. So, in this point, whenever the particle's displacement is here, in this point the particle is actually having a large amount of kinetic energy. Okay. Now, you see, when the particle is actually moving towards this direction, for example, let us say again the particles, at some instant I am actually thinking that okay, the displacement of particle is actually here, or the particle's displacement is actually here. Let us say I am taking this one, and in real time this is also maybe at some point like this x1. Okay, x1. At this point, what is the potential energy? The potential energy is this one, because this is the u of x1. at this displacement, and so this is actually this one, and this is the total energy. So, again this amount of energy, this amount, so this is potential energy and this is total energy. The difference between them is the kinetic energy at this displacement. Okay. Now, we just consider of this point. At this point you see its total energy and the potential energy at this point, let us say this is minus x 2. So, u of minus x 2 is exactly equal to u 1. So, then what will be the kinetic energy at this point? The kinetic energy will be 0. Okay. So, if we say that when the particle is having some displacement here, let us say in this negative direction minus x 2, okay, after that the particle is no longer having any kinetic energy. I mean at that instant the particle is not having any kinetic energy. Okay. So, the particle cannot have any motion, I mean cannot have. So, at this point where the particle is not having kinetic energy, you can see that the particle actually cannot go beyond this, because this is the limit of this potential well. Okay. And that is why you say that this particle actually you can now make an equivalent image that in this direction. So, if you just now think with respect to this origin here of this x displacement axis, you can actually think, given a value of energy, total energy E 1, if the particle reaches minus x 2, then after that the particle cannot go anywhere which is more negative than minus x 2. Okay. So, this is the limiting value of displacement with this energy, because at this point the particle is exactly having its total energy and potential energy to be equal, and it has 0 kinetic energy. So, the particle actually momentarily becomes at rest. This is exactly the picture where a particle really is moving and gets hit by a wall, and then momentarily it becomes at rest, and then the particle actually reflects back, and that is why this point is known as a turning point. Okay. Of course, once again a turning point in potential diagram is not really saying that the particle is in real time is actually reflect back. Okay. The particle can be actually I mean do some other type of motion. Okay. And it is not simply just going and then reflects back into instantaneously, but the point is that with respect to this representative picture, as a function of displacement, you will see that it is the reflection with respect to the displacement. So, after this point displacement cannot go further, I mean cannot increase further. In case of this type of simple harmonic oscillatory potentials, if you let us say give some energy E 1, you can see it has turning points in both the directions. So, for example, starting from 0, if it goes in this direction up to this amount, let us say some x 1 and here some minus x 2, in both cases, and this is its potential energy curve, then at both these points the total energy becomes the potential energy, and that is why in both the cases the particle momentarily becomes at rest, and it has actually 2 turning points. Here I have one turning point here, another turning point, to be very honest at this point does not exist, because here on the other hand if the particle is going to increase its x in the positive x direction with respect to the displacement, of course, you will see that there is no other situation where with this energy the particle can have a limiting value of its displacement, and actually theoretically it can go to infinity, and that is why in this direction the particle is actually bounded by this displacement minus x 2, in this direction it is bounded by infinity, that means it is not bounded. Okay. So, so this particle has bounded motion in the left direction for negative x, and when it is just going to increase, it is unbounded. But of course, you understand something which is a mixture of bounded and unbounded cannot be fully bounded. So, it is more logical to call that is an unbounded motion. However, if the particle is now in this regime, that means the total energy which I give is actually E2 value, which is surprisingly negative also, you can see. Okay. It is a negative value, the total energy is negative value. Now, you know that the kinetic energy cannot be negative. So, but the potential energy can be negative. Actually, you will see for when we will talk about central force, these things will be much more comprehensible. That is, if you have a total energy which is equal to negative, that actually said that you have potential energy dominated region, and if the kinetic energy is dominated by the potential energy, basically where you can see that you will have a bounded motion between these 2 points. So, that means in this case, unlike this first one, you have a bounded motion in this direction starting from x is equal to 0, and also in this direction. Okay. So, you have the particle will have some bounded motion between some x to between some x1 star to some x2 star. Okay. So, in these two directions its displacements are actually bounded. So, whenever you see, whenever you just take a snapshot of the particle, again you do not care about at which time instant you are taking the snapshot, but whenever in the motion, during the motion of the particle you take a snapshot and you measure the displacement, you will always see the particle is actually having a displacement which is the magnitude of the displacement which is lying between this and this value. Okay. So, this is bounded in 2 points. So, this is a case where you have 2 turning points. So, whenever a particle has 2 turning points, okay, then we can talk of a bounded motion. Okay. But of course, whether a particle is undergoing a bounded motion or an unbounded motion, this depends on mainly on 2 things. The first is the nature of the potential curve, and the second thing is that the amount of the total energy, total mechanical energy which remain conserved during its motion. Okay. This type of situations can also be understood can also be understood when you will do several type of potentials, and actually for example, if you have a potential like this, okay, and then you will actually understand that whenever you have an energy, total energy which is E, then you see that even with this thing you have bounded motion between this point and this point. Okay. However, if you are in this regime, you still have two turning points, but if you have in this regime your energy is like at this level, then you have actually bounded motion between these two and again these two. Okay. So, this is a more complicated situation, and this type of situations are also very interesting in physics. So, I mean whenever we will talk about in next week, when we talk about central force, we will actually talk about some interesting features of that, and also in your assignment I will give you a little bit twisted problem on this topic. Okay. Thank you.